All right, welcome back. So, chapter 15, uh, section 2, part 2. We're continuing to talk about weathering. And with chemical weathering, especially if you have the entire bedrock be based on some type of rock like limestone that dissolves, you get these really unique landforms called karst topographies. Okay, and so what this means is if you have an area where the underlying rock is mainly limestone or carbonate, it weathers in certain ways that creates these really interesting, unique features. Okay, mainly through the reaction of groundwater, so water in the ground, and it is famous for one thing. It's famous for are subterranean or underground caves. So what happens is quite simply, rain and water soak into the ground, and the water becomes acidic through carbonation we talked about. And what happens is the acidic water, when it hits calcite, which is one of the minerals in limestone, it basically dissolves it. It turns it into mush and eventually makes it water soluble and washes it away. And by doing this, it follows the easiest way through. And so what that means is if you have a big chunk of limestone, there's a little crack in it, right? The water's going to find that crack, seep in, make that crack wider and wider, and over time, you're going to see the certain types of karst topography. So we look around the world and we can see these areas in red are karst regions. So right here, if you've ever been down through Kentucky or Tennessee, the Mammoth Caverns are down there, huge. Large areas here of Asia and Europe as well. So the first thing we talk about is a sinkhole. Sinkhole is just like a big pothole on the surface of the earth. And what happens is the rock underneath just wears away and it just kind of sinks into the ground. Like almost like I guess you could almost like a big puddle, right? And if that sinkhole goes down deep enough, the water from either the ground soaks into it or the rain and it fills. So you get these sinkhole lakes, okay? Now sometimes what happens is a sinkhole forms when underneath the surface of the ground, the rock is wearing away, like a cave. And if it keeps on continuing to happen and the cave gets bigger and the roof of the cave gets closer to the surface of the earth, it gets too weak and it just collapses in. So they call it a collapsed sinkhole. And these can be spectacular because right here, here's a picture of a house. Underneath, a sinkhole formed. The house, people didn't know that, and all of a sudden one day their house just falls into a sinkhole. So here's an example. Here's the limestone. Here's the water table. Some sinkholes form on the surface and the limestone dissolves. And there's sinkholes right here. Florida, almost the entire Florida peninsula is limestone. And so if you look from above, you see all these little sinkholes. They look like basically like almost like holes in Swiss cheese, if you will. And quite simply, the ground is just dissolving underneath it. So it also forms caverns and collapsed sinkholes. So here is a situation where the rock is mainly limestone. Some water drips down through this crack, dissolves, eats its way through, finds right here. And maybe there was some water flowing this way. So this is a big, huge cave, and the water meets that cave, and now you've got a little bit of a little cavern. It's getting bigger, and this dissolves more and more. And eventually, this gets bigger and bigger. As it gets close to the surface, the top will fall in. And these can be quite large, actually. Now, a cenote is another type of karst topography feature. This is famous in the Yucatan Peninsula. And the cenote is just really, it's a collapsed sinkhole, but the bottom of it is so deep that it's below the water table, so it just fills with water. So in the Yucatan, near Cozumel and Cancun, the only surface water, there are no rivers, are these basically filled in cenotes. And it can also make beautiful caves and weird underground valleys. So here you have, again, a block of limestone, and the water table's right here. So the water's dissolving, eating away all these gaps in the rock. But maybe something happens, and the water table drops, and now these caves are empty and dry. And so you can actually see these caves and people explore them. But what happens if, at the same time this happens, erosion wears away the soil in this top layer of rock? You actually get this kind of weird valley right here, kind of in between the rocks. I know it's kind of half buried in my face, but one of the most unique ones is the Plain of Nullarbor. This is in southern Australia. And because in a limestone karst topography, all the water, once it goes into the ground, finds the cracks in the limestone and basically dissolves it. There's very little, if any, surface water. There's rarely ever any rivers or lakes, because all the water that would be on the surface, like it is here, just basically dissolves the rock and forms these huge underground caves. So this is what it looks like from space. This is about from here to here across it, roughly, I would say 120 miles, and it's one of the flattest expanses on Earth. And it looks like this, just mile upon mile of flat scrubland, perfectly flat, almost like a pool table. The world's straightest highway runs across this. It's a straight road for over 100 miles without a single turn. Another one that's really bizarre is the disappearing stream. So oftentimes you'll have these layers of maybe limestone, which is water soluble, right? And then shale, which does not wear away very well, and limestone. So limestone, shale, limestone, different levels of rock. So here you have a limestone top layer, and all the groundwater soaks into it. But when it hits the shale, shale doesn't dissolve. So it just sits there and flows over it. And if there's maybe like the side of a hill where these rock layers are exposed, then that water will come out like a stream or waterfall. Now, if the waterfall goes down deep enough and finds another gap in the limestone, like down here, it'll eat away an underground stream. So what happens is you get this. The stream emerges here, runs down this waterfall, and then disappears back underground here. Limestone pavements, if you had a layer of dirt over this that eventually wore away and revealed the limestone had been carved by water, you'll get this. It looks like people put in these rocks like on purpose, almost like pavers. So people used to think these were mythical giants that built these. It's actually completely natural. A cockpit karst is another type of form. You get these kind of rounded hills of rock. So kind of interesting. This one is from Madagascar. And here you have, in between the limestone, you have vertical sheets of rock that are very, very resistant. And they are what's left behind when the limestone wears away. Almost like stone fences that can be 20 or 30 feet tall in parts. And then my favorite is a tower karst. And this almost looks like it's from the movie Avatar or some weird video game. These huge towers of rock that are maybe 10 feet wide but 200 feet tall. And what happens is these were once all one solid layer of rock, but there were joints between them, cracks that wore away with water over millions of years. And this is what's left. Now, a subterranean karst, this is just subterranean, anything that happens underground. So caves often form underground. We don't usually see them until something happens to maybe expose the entrance. But one of the most interesting speleotherms, which is just a fancy name for a cave feature, is the stalactite, or the stalagmite. You've probably heard of both. And the stalactite are those stone fingers that look almost like icicles that hang from the sides of caves. And what happens is they form over millions and millions of years. Water is constantly dripping through the rock, the cracks, the joints, eating it out. And as it does, it dissolves the rock slowly. And so in that water is a lot of dissolved minerals. And as it drips, and right when it drips, it leaves behind the minerals. So the minerals get stuck there. And it forms a soda straw, which over time adds layer upon layer upon layer. And in a couple 100 million years, you get a stalactite, which looks like a rock icicle. And it's a lot similar to how an icicle forms in winter, right? The water drips off the edge of a house, off a roof, and slowly freezes, and more water drips down the ice. Same kind of principle, actually. Now, that water that fell off the end of this little baby stalactite soda straw, little pool here, over time, that water will dissolve or evaporate, and what's left behind are the minerals. And so a stalagmite forms, kind of the opposite of stalactite. And if they keep on going, they will eventually meet in the middle and form a limestone column. So they're really beautiful. They look like, here's one from Italy. Stalactites hanging from the ceiling, stalactites reaching up. If you were to cut one in half, you would actually see the initial soda straw stage, that initial hollow column, and just the year upon year upon year of layers. Unfortunately, a lot of people when they visit a cave will want to touch these. They're beautiful. But one thing that happens is the minute you put your hand on it, the natural grease in your hand actually disrupts that and makes the water flow faster, and the stalactite stops forming. All right, so we're going to head to the next one. Mass movement, unstable ground, landslides, mudslides, avalanches, and such. So why does mass movement occur? Mass movement is just something, any kind of movement of any solid material, so rock, soil, ice, or debris downhill. Gravity. It's gravity caused. Okay? What causes it? Lots of different things. First of all, how stable is that hillside? What is it made out of? Is it rock? Is it gravel? Is it sand? Do earthquakes shake it? Do rivers wear away at it? Has it just been raining and the rain has turned the dirt that is rock hard into mud? Have we cut down all the trees and the roots no longer hold it in place? Many features. Okay, but the big thing that kind of starts this is we have to think about this idea of slope stability. The side of a hill, if it's stable, it doesn't move. If it's unstable, you have things going downhill. And what causes that is this idea of resistance force. So let me kind of talk about that. Resistance force. If you stand on the side of a hill and you don't slide down, maybe your feet are at an angle, that means that you have a greater resistance force in your shoes right now than gravity. In other words, your resistance force is stronger than gravity, so you don't slide down the hill. But if you've ever stood on the side of a sand dune or a really steep hill and you can't help but slide down the hill, then gravity or the gravitational force is stronger than the downslope force. Okay? And so anytime you do something to either increase gravity or do something to decrease the downslope force, you're going to have a mudslide. Now, we don't really have a way to change the force of gravity right now. That's kind of Star Trek stuff. So basically, it becomes more about a factor of something that increases the downslope force. And when we have stability, we have what's called the angle of repose. So the angle of repose is how steep will that side of a hill be left to its own devices. So think about when you were a kid and you go to the beach, you'd play with sand, right? You'd pull the sand up in your hand and you let it kind of fall through and it would form that cone, right? Now sand has a pretty smooth feature. You really can't stack it up, right? So if you pour sand, you don't get a steeper angle, you just get a taller hill with the same angle. So in other words, the angle of repose for sand is 30 degrees. But if you were to put gravel or rocks together, you can kind of make them, build like a little bit of a tower. Or what if you added water to the sand and made it more like a thick mud? You could have a steeper angle. And here's what we're talking about. Here's the slope, and here's a rock. Now, imagine this rock is your shoe, right? Hitting the ground. And resistance force is how much, you're pushing down, how much traction do you have on your shoe? Do you have on, ballet flat bottom slippers? Do you have on hiking boots with spikes? That would increase that. But if the resistance force is stronger than the force of gravity, you're not moving. It's a stable slope. But if something happens to decrease that, maybe the ground you're on gets wet, and so it becomes loose and muddy, and your spikes and your shoes don't hold. Or you gain weight, and you get bigger. Something causes gravity pull harder, then you will slide down slope. The angle of repose is the steepest that will be based on the material available. So we kind of talked about this. These are for you to read on your own. I'm not going to go through these, but these are just different things that can affect it. So let's talk about ground saturation as an example. If a hill is made of really hard packed clay or dirt, it's pretty stable. But if the rains come in, it's adding water and it turns that dirt into mud and you get mudslides. So something happened to change those forces. So mass movements can happen anywhere from instantaneously, like rock falling off the side of a mountain, to taking hundreds of years and occurring so slow that you don't really even notice it. And the slowest one is soil creep. And we're going to talk about that in a little bit. But basically, we're going to talk about all these different types. They range in speed from slow to fast. So soil creep is the slowest. And they call it creep because you probably won't even notice it. It happens year after year. And what happens is, this is caused mainly by the movement of soil when the winters freeze it. So here is a little piece of rock right here, right? Now, in the winter, any water in the ground expands, so it pushes it straight up. So the ground freezes and it gets pushed up because of the expansion. Okay, so now it's here. But in the spring, as the soil melts, it falls slowly back down to where it is, here. And then next winter, as it freezes, it gets pushed away from the rock. It goes back and forth. So you'll notice that it's going like this. It's actually going slowly forward over time. So the soil as a whole just slowly moves this way. It doesn't all at once, and it happens so slow that you wouldn't notice it, but over time you get images like this tree right here. It actually bent the tree because as the soil moved, the tree kind of started to go like this, but the tree kept on growing. You'll see cracked telephone lines, houses sagging. It'll slide over the streets. This one's called solidification. It's really interesting. It's when whole sheets of earth move together at once. It almost looks like sagging, like laundry. Reminds me of having to fold the towels or something. Now a slump happens a little bit faster. And normally what happens is you have this hard bedrock underneath and the softer dirt on top. And something happens right where this dirt meets this rock where it loses its grip, and so it slides down as one big chunk. And so what happens is it basically breaks at the head scarp and goes and slides right down. And it mainly moves as one kind of solid unit in comparison to the rest. Maybe in blocks, but for the most part all together. And at the top of it's called the head scarp, and I know you can't see it here, but the end of it, I love what they call it the toe. Okay? So sometimes they call them rotational slides because they kind of rotate as they go down, but for the most part, slumps is the most common term, right? And it looks like this. Here's one in California. It broke right here, and this chunk right here in the middle just kind of slid down as one. As we get a little faster, we get into slows and landslides. Landslide is just any kind of movement of rock or dirt and debris down the side of a hill. So it could be rock, dirt, trees, pigs, cows, cars, whatever gets caught up and pushed down a steep slope. Okay. If it's made mainly of mud, then it's called a mud flow. And because mud can be quite liquidy, it can actually move quite faster. But a debris flow is very similar. This one, there's a lot of other things mixed in. So there's a lot of rocks and vegetation. It can be called a debris flow. Know that these are all basically the same thing. These are just kind of refining them. A landslide can be a debris flow, and a debris flow is a landslide. Lahars we talked about. These are volcanic in nature. So a volcano will erupt, and the heat from the eruption melts any ice on top of the mountain and causes it to flow down. So again, a lahar is nothing more than a volcanically caused landslide. A rock slide is even faster, and here it's mainly just rocks. So up in high mountains where there's no soil and there's no trees and nothing but rocks, they just break and slide right down much faster. So a debris slide is a rock slide that has rocks and maybe some chunks of soil and vegetation. And the one you're probably most familiar with is an avalanche. Right? An avalanche is usually with snow. So snow on top of a mountain comes down the side if it brings anything down with it. Now, Hawaii, we think of Hawaii are these islands in the Pacific Ocean. But as we've talked about before, here's the big island of Hawaii. This part of Hawaii is 14,000 feet above the water. But when you get to the shore right here, from here, all the way down to the base, is another roughly 15,000 feet. So landslides happen all the time in these islands. But what happens is they keep on going down. We don't think about what happens once they hit the water. They keep on going. Over here, this is the island of Oahu. Oahu used to be twice as big millions of years ago. One of the things that happens to the volcanic islands is as they no longer erupt, right, these volcanoes begin to break down. And actually, over time, this part broke off and slid down the north side. And there's actually evidence of like this huge 20-mile long avalanche right here. And actually, this is what it looks like. Here's the scarps that were left behind, and everything just slid down deep into the ocean. So a snow avalanche, what's probably what most you think of is composed of snow. Avalanches can be just snow, but if there's areas near forests, so they could have debris in it, ski shacks, skiers, unfortunately. So debris avalanche, mainly still snow. Now, avalanches are deadly for a couple reasons. One, they're extremely turbulent because the snow is quite light and it allows air to mix in with it. So it comes down, and this turbulence of snow and ice can actually break apart trees and rocks. And the other thing is that when it finally settles, what is snow but water? People do suffocate over time. What happens with an avalanche is the snow is on the top of the mountain, right? And it just builds up and builds up and builds up. And if the snow gets too heavy, it'll literally just slip down the side. So in other words, the snow got so heavy it overcame that compressional force that held it to the mountain. The areas that have avalanches tend to have them year after year. They have constant snow. It always builds up. So where we see that happen, it basically forms like a chute. The snow on each side kind of forms a slide, called an avalanche chute. You can see right here, this area is kind of like a small dip in the mountain, and the snow is constantly having avalanches here every so often. Rockfall is the fastest, and it's just literally a piece of rock falling down the side of a mountain. So it happens on high mountains or cliffs that are vertical, so you have that kind of very steep drop. It also happens where we cut through to make road cuts. So sometimes when we're building roads in the mountains, instead of going over the mountain, we cut through it like a ditch. And this is caused by things like frost wedging or other rocks falling that break apart rocks. And as these rocks fall down the side, when they finally reach the bottom, they form like a debris pile. They call that a talus. Okay? Yosemite National Park in California is actually a glacial valley. The glacier has long since melted, but it has very steep edges. And so there are rock falls every year. These colored dots indicate what time of year, and the size of the dot tells you how big. These are sometimes pretty big rocks falling off the sides of the mountains. And when all that rock falls down and finally stops moving, you get this big, huge talus right here. And talus is just the rocks that have fallen off. So there's the rock kind of the rockfall chute. They also call this a talus apron around the bottom of the mountain. So all of these things, weathering and mass movement, they act together. They act with each other. They make things faster. They make things slower. But in the end, what they do is that every time the Earth builds a mountain or a volcano and builds things up from the geothermal energy of volcanoes that we talked about, weathering and mass movement counteract that. So the Rocky Mountains are being built today, as you saw in that video, but over time they will erode. The Himalayas are today the tallest mountains in the world. They will eventually wear back down. And it's kind of funny. We come back to the Grand Canyon quite a bit because it is actually a very good laboratory for a lot of this. In this picture, you can see pretty much almost everything we talked about. So plate tectonics. As your movie showed you, right, millions of years ago, the North American plate began to lift due to various actions. And that lifting elevated the Colorado River, which gave it more energy to cut down to the sea and dig this 1 mile deep canyon, right? Weathering. If you look at the Grand Canyon sides, some of the cliffs are steep and some are shallow. Different angles, different rocks wear differently. You see all these various joints in the rocks which allow weathering to happen. Some rocks are chemically weathering. This orange color you see here is actually rust. These rocks have a high iron content and they're rusting out. These rocks are being broken apart by frost wedging. Every year a little bit more frost breaks in there. In fact, that frost wedging has formed this little rock sticking out that might fall off and roll down. It's a rock fall. Rock slides coming down form these big huge talus angles. The next thing we're going to talk about in the next chapter is erosion. And here, all that weathered material eventually falls down into the Colorado River, which erodes it and moves it. So that's actually next chapter. So I'm going to end this part right here. We're going to come back with the next video in just a little bit. So I'm going to pause this. So go ahead, get yourself a cup of coffee, and we're going to talk about deadly mass movements to end the chapter. Woohoo!